neural control of exercise muscle 2, nerve impulse or action potential. Neurons are referred to as excitable tissue because they can respond to various types of stimuli and convert those messages to an electrical signal called a nerve impulse. This lecture covers how the electrical impulse or action potential is generated and how it travels through a neuron. So let's focus on the nerve impulse or action potential. The plasma membrane is composed of a lipid bilayer. Its hydrophobic nature prevents the diffusion of ions across the membrane. Neurons are surrounded by a plasma membrane that is impermeable to ion. This property allows a neuron to maintain different concentration of ion between the inside and outside of cell. In a typical neuron, there is a large difference in the concentration of ion, such as sodium and potassium, between the intracellular and extra environment. In addition, the interior of the neuron has a high concentration of large negatively charged protein. And banana, right, like most fruit and vegetables, are high in potassium and low in sodium. So there are salts, like sodium, in seawater, right? So it helps you memorize an intracellular environment like land has banana, so more potassium, and seawater, like an extra environment, has more sodium like salt. The only way ion can move across the lipid bilayer is by passing through specialized channels. These channels are transmembrane pores that permit the movement of particular ions while excluding others. Such channel can be in an open or closed state. Most ion channels are closed. However, some potassium channels are open, permitting potassium to diffuse out of the cell down their concentration gradient. In this case, these potassium channels are potassium leak channel. So I just put the nickname, potassium leak channel. So sodium channels are normally closed, and thus sodium cannot cross the membrane when the neuron is at rest. The internal concentration of potassium is higher than the external concentration. First, a diffusion force drives potassium along their concentration gradient toward the exterior of the cell. However, the movement of potassium out of the cell increases the internal negative charge. The positive charged potassium are attracted of the internal negative charge, and this electrical force pulls potassium back into the cell. The diffusion and electrical force eventually come into balance, and an electrical potential or voltage is reached at which the electrical force exactly balances the diffusion force. At this point, there is no net movement of potassium into or out of the cell. The electrical potential across the membrane can be measured by inserting an electrode into the cell. A neuron at rest has a voltage difference of about negative 70 millivolts across membrane. This value is the neuron's resting membrane potential and is governed by the relative concentration of ion spaces between the intracellular and extracellular spaces. Sodium potassium pump actively transports 2 potassium into and 3 sodium out of the cell to maintain the resting membrane potential. This pump uses ATP. Practice quiz 1. The resting potential of a neuron is due mostly to open sodium channel or open potassium channel. Which is the leak channel? Yes, potassium channel. So answer is open potassium channel. Potassium channels are the most common open channel in the plasma membrane of resting neuron, As a consequence, resting neurons are more permeable to potassium ion than to any other ion. Practice quiz 2. At rest, the interior of a neuron is negatively charged relative to the exterior. This negative charge is due to mainly to the interior of the neuron contain a high concentration of large, did you remember? Yes, negatively charged protein. Inside more negative, outside more positive, because the interior of the neuron contain a high concentration of large negatively charged protein. Practice quiz 3. At equilibrium, when the neuron is at rest, the concentration of potassium is higher inside the cell, but the diffusion force driving potassium out of the cell is balanced by an electrical force keeping potassium from leaving the cell. Resting membrane potential is negative 70 millivolts. Did you remember? The action potential neurons communicate over long distance by generating and sending an electric signal called a nerve impulse or action potential. Let's focus on action hillock because the action potential begins at the axon hillock, where the density of voltage gauge sodium channel is greatest. During depolarization, sodium moves into the neuron. As the axon hillock depolarizes, voltage gauge channel for sodium open rapidly, increasing membrane permeability to sodium. Sodium moves down its electrochemical gradient into the cell. As depolarization reaches threshold of negative 55 millivolt, the action potential is triggered and sodium rushes into cell. Membrane potential reach positive 30 millivolts on action potential. If the stimulus to the axon hillock is greater enough, the neuron depolarizes by about 15 millivolts and reach a trigger point called threshold. At threshold, an action potential is generated. Weak stimuli that do not reach threshold do not produce an action potential. An all or none event, right? So, will there be an action potential? No, this depolarization has not reached threshold. Oh, will there be an action potential? Yes, at negative 55 millivolts, the membrane is depolarized to threshold and action potential is generated. Threshold for this neuron is negative 55 millivolts. Only when a neuron reaches threshold, a positive feedback loop is established. At threshold, depolarization opens more voltage gate sodium channel. This causes more sodium to flow into the cell, which in turn causes the cell depolarize further and opens still more voltage gate sodium channel. This positive feedback loop produces the rising phase of the action potential. The rising phase of the action potential ends when the positive feedback loop is interrupted. The inactivation of the voltage gate sodium channel, the opening of the voltage gate potassium channel. At the peak of the action potential, voltage gate sodium channel begin to inactive. At day inactive, the inward flow of sodium decreases and the positive feedback loop is interrupted. The voltage-gated potassium channel respond slowly to depolarization. They begin to open as the membrane depolarizes, but respond so slowly that they become fully activated only after the action potential reaches its peak. As potassium moves out, depolarization ends and the positive feedback loop is broken. With less sodium moving into the cell and more potassium move out, the membrane potential becomes more negative, moving toward its resting value. This process is called repolarization. The slow voltage gate potassium channel remains open after the cell has repolarized. Potassium continues to move out of the cell, causing the membrane potential to become more negative than the resting membrane potential. This process is called hyperpolarization. By the end of hyperpolarization, all the potassium channels are closed. Now resting membrane potential, but still inside more sodium and outside more potassium, so sodium-potassium pump actively transports 2 potassium into and 3 sodium out of the cell to maintain the resting membrane potential. While the neuron is generating an action potential, it cannot generate another one. Many sodium channels are inactive and will not open no matter what voltage is applied to the membrane. This period is called the absolute refractory period. Immediately after the absolute refractory period, the cell can generate another potential, but only if it is depolarized to a value more positive than normal threshold because some sodium channels are still inactive and some potassium channels are still open. This is called the relative refractory period. The exolemma is the cell membrane of an axon. The similar term exoplasm refers to the cytoplasm of an axon. The exolemma is responsible for maintaining the membrane potential of the axon and contain ion channel through which ion can flow rapidly. After an action potential is generated at the axon hillock, it is propagated down the axon. Positive charge flow along the axon, depolarizing agents area of membrane which reach threshold and generate an action potential. So summary, the action potential is an all or none event that can travel for long distance because it is a regenerative electrical signal. When the axon hillock is depolarized to threshold, an action potential is generated. Voltage gate channel open, thereby increasing permeability of the neuron first to sodium and then potassium. As sodium moves rapidly into the neuron, it produces the rising phase of the action potential. As the inward movement of sodium slows and the outward movement potassium increases, the membrane repolarizes. Immediately after the action potential, the neuron cannot generate another action potential during the absolute refractory period. During the relative refractory period, it can generate another potential only if stronger stimuli arrive at the axon hillock.